Okay, in this integral we look at what is called the Laplace's method. This is a method which is designed for integrals of the following form. So we consider integrals of the form so from a to b, f of t e to the power lambda phi of t dt. So we're going to look at the asymptotic approximation of these integrals as lambda tends to infinity. Here the two functions f of t and phi of t are assumed to be analytic in the interval a to b. So those two functions excuse me, are analytic in this interval here. Now this method is based on the fact that as lambda goes to infinity, the impact of this function here is going to be amplified. So basically this integral here is going to be dominated by what happens here, and in particular to that function there. Actually, so the point in this interval where this function is maximum is the one that is going to dominate the behavior of this integral here. So the major contribution of this integral as lambda goes to infinity will come from the neighborhood of the point where phi is maximum, of the point where phi is maximum, of the point where phi is maximum. Now there are going to be three cases that we are going to look at. There are three cases, and the three cases, let's just show them graphically. So in the first instance, phi could have, so this is point A, this is point B. In the first instance, function phi could have a maximum point at t naught, where t naught is between A and B. Then the other two instances phi, so in case 2, phi could have a maximum at the point t equals to a, or phi could have a maximum at the point t equals to b in case number 3. So this is going to be our case 1, this is going to be our case 2, and this is going to be our case number 3. So let's look at case number 1 in some detail now. Yeah, so case number 1. So if phi of t has a maximum at an interior point t naught, then we know it means that phi at t naught prime, phi prime at t naught is going to be 0, and the second order derivative at t naught is going to be less than 0, because we expect the function to be concave down at that point. Then in the neighborhood of t naught, we can expand phi in a Taylor series. So phi of t is going to be phi at t naught. The second term is going to be 0, the phi prime term. Then the next term is going to be 1/2 t minus t naught squared phi double prime at t0. So if we just take those two leading terms, so then the integral is going to take the following shape. So we've got integral from a to b, f of t e to the lambda phi of t dt. Now, so if we just do the leading order expansion of f at t naught, it's just going to be f of t naught, and then in the exponent there we're going to have lambda into phi at t naught plus 1/2 t minus t naught is going to be phi prime at that dt. The f at t naught we can factor out. Also this term we can factor out because it does not involve t. So e at phi, e to the power phi at t naught, which we're going to denote phi naught. So just for brevity, we're going to denote this phi naught. We're going to denote this one phi 2. Then this is going to be the integral from a to b e to the lambda over 2 t minus t naught squared phi 2 dt. Let's denote this I of lambda again. Then we're going to make a substitution. Remember that this term here is negative, so that means this whole thing here is negative because lambda is positive. This is a squared term, so this whole term here is negative. So what we want to do is we're going to make a substitution. We're going to let u be equal to negative lambda over 2 t minus t naught squared phi 2. Okay, so which means this whole thing is now a positive term. Then if so this is u squared, so u is just going to be t minus t naught into the square root of negative lambda phi 2 over 2. So this is fine here because this is a positive number, and then it means dt is going to be negative 2 over lambda phi 2 du. Okay, and then the integral is going to become so it's going to be integral from when t is equal to a, so we'll just plug in a here, so that's going to be a minus t naught times that square root, and then on t is b minus t naught times that square root f of t naught e to the lambda phi naught, and then we're going to have e to the minus u squared. Okay, because this term here just becomes negative u squared from there. Then we are going to have that square root of negative 2 over lambda phi 2 du. Then let's just talk about this here. So as lambda goes to infinity, so this is what's going to happen, which is a bit similar to what we looked at in the previous section. So If our function is a bit like this, for instance, then what's going to happen is that as lambda, so that's our phi, then lambda times phi, so as lambda becomes bigger, and these values of phi that are bigger are going to be amplified, and so increasingly the values that are away from T naught are going to become more and more negligible, while the bigger values in the neighborhood of T naught are the ones that are going to be amplified. So at the end of the day, just this region next to T naught is going to be important, while the rest, actually, this is going to be, compared to that, it's going to be like going to zero, if you like. So then integrating from here to there is going to take all the contribution. So whether we integrate from here to there or from negative infinity to infinity, then those two should be comparable, because all of the contribution is just from here. So what's going to happen is, in our integral, this, which is negative, we're going to adjust to negative infinity, and this one we're going to adjust to positive infinity. So our integral is now going to look something like this. So we are going to have f at T naught e to the power lambda phi naught, and then we are going to have integral from minus infinity to infinity. Just one moment, there's another term here. There is the square root term, negative 2 over lambda phi 2, then integral from minus infinity to infinity of e to the minus u squared du, and then there's going to be some transcendentally small terms there. Well, from our discussion on gamma functions, we've already established that this integral here is equal to square root pi. So from there, this thing is simply going to give us so f of T naught e to the power phi at T naught times the square root of negative 2 over lambda phi double prime at T naught. Okay, so what we are saying is that, in summary, this integral here, a to b f of t, is going to behave like f at T naught e to the lambda phi at T naught times, so this is 2 pi here, is lambda goes to infinity. All right, so that's the statement of Laplace's method for the case where the function has got a maximum, the function phi has got a maximum at an interior point t naught. Okay, we're now going to look at the case 2 where the function has is a maximum at t equal to a. So suppose this time that phi of t has a maximum at t equal to a. Then if we expand this as in a Taylor series around the point A, these are the first two terms that we are going to have, t minus a phi prime at a. And then of course we can do the same thing. So the leading order term for f is just going to be f at a, and the integral is going to take the following form. So integral from a to b f of t e to the lambda. Okay, so this is going to be like the integral from a to b f of a, then we're going to have e to the lambda phi of a t minus a phi prime at a dt. Now the only term that involves t here is this one here. All the others are constants. So if we factor those ones out, we're going to have f of a e to the lambda phi at a, and then integral from a to b e to the lambda t minus a phi prime. This is straightforward to integrate. It's just integral of e to the constant times t. So we can do that integration. It's going to be e to the lambda t minus a phi prime at a, all divided by lambda phi prime at a evaluated between a and b. If we substitute, so it's going to be f of a e to the lambda phi at a. So when t is b, let me just bring this one this side. When t is equals to b, is going to be e to the lambda b minus a phi prime at a. And then when t is equal to a, this is going to be 1. All right. Now, the only way that phi can be a maximum at A is if the derivative of phi at A is negative. So this is t equals to A, that is phi there. So the only way it can be maximum is if that derivative is negative. So that tells you that this thing is negative here. So that means in this group of terms, this term is positive, this term is positive, this term is negative, so this whole term is negative. So as lambda goes to infinity, this is going to go to 0. So that means that expression there is just going to simplify as follows. So we're going to have negative f at A e to the lambda phi at A divided by lambda phi prime at A. So that's going to be the asymptotic value of that integral if the maximum phi has a maximum at t equals to A. The third case, if phi has a maximum at t equals to B, excuse me, then this integral as lambda goes to infinity is going to behave like f of b e to the lambda phi of b divided by lambda phi prime at b. So this is as lambda goes to infinity. Okay, this derivation is pretty similar to the case 2 derivation, so we're going to leave that one as an exercise. Okay, the next video we're going to look at some examples then of the application of Laplace's method